Are we all tired? A little bit. So I arrived here 2 days ago, 27 hours flight from Australia. About now is the time is 11:45 p.m. So it's about 2 hours after my normal bedtime. So hopefully my presentation will be interesting, because if it's not, I'm going to be the first person falling asleep. So this presentation is called Streaming to a New Jakarta EE. My name's James Roper, by the way. Why have I come all the way from the other side of the world to talk to you? I'm an Eclipse committer. I am the lead of the MicroProfile Reactive project. I work for a company called Lightbend. Anybody here heard of Lightbend? A few. So Lightbend is the company behind Akka, Play Framework, Lagom, and the Scala programming language. We also were founding, or created the Reactive Manifesto, founding members of the Reactive Streams initiative, and pretty much anything reactive, usually Lightbend has its fingers in it somewhere. So my role, I'm the senior developer in the Lightbend office of the CTO. Office of the CTO is a kind of weird team in different companies. Basically it means the CTO has a crazy idea and I have to go and make it kind of happen. I co-created Lagom. So Lagom is Lightbend's reactive microservices framework. And I used to be the tech lead of, prior to that, the tech lead of Play Framework, which is a high productivity reactive web development framework. Prior to that, I worked for Studie Outset. If there's any Germans in the room, probably be snickering. It was a social network. I joined at its peak, and then it started going downhill. So I probably want to move back to Germany someday, would be cool. So any startups want me to destroy their company, just let me know. And I worked for Atlassian before that, and I used to use, I cut my teeth in my career on J2E 1.4. I actually haven't used Java EE in anger since, like EJB 2.1 and some of those lovely things. So what are we going to look at today? The first thing we're going to look at is why we need streaming. The first part of this talk is very architectural, not actually related to really Jakarta EE, MicroProfile, or anything like that. We'll contrast monoliths to microservices. We'll see what the differences are, what the differences in constraints are, and the technical challenges when we take the traditional approaches that we used in monoliths that we have when we try to apply them to monoliths, to microservices. And we'll look at how streaming can solve some of these problems. We'll also have a demo, and in the demo we'll take a look at some in-development specs for MicroProfile. We'll take a look at some ideas for possible future specs, and we will see streaming in action. So monoliths have allowed us to take consistency for granted. You can think of it like oxygen, okay? So when I go, say, from home to work, I don't need to, it's incredibly important that I always have oxygen to breathe, because otherwise I'll die. But I don't think, okay, where am I going to get my oxygen from when I get to work? How am I going to breathe on the way to work? I don't think, I just take it for granted. It's incredibly important, but I take it for granted. And consistency is somewhat the same in monoliths. We take it for granted. We don't even realize how important it is to us, because it's incredibly important. Very few business applications are able to cope with inconsistent state. So for example, an order service saying that this order is submitted, and the payment service saying this order doesn't exist, because then you don't get paid for the order. Okay? Consistency is incredibly important, but monoliths have allowed us to take it for granted. So it turns out when you have a single database, the world is very easy. And the reason for this is that we can use transactions. We can use ACID transactions. All of our operations can be done inside a transaction. And transactions do this by giving us this illusion of a single consistent current state. There is a concept of what is the state of the system now? Okay, what can I do now? What does it look like now? And that idea of now is all consistent. Okay, you're not going to go to the order table and see that the order is in the awaiting payment status and the payment table to say that it doesn't exist. You have this consistent state of now, and it all is consistent. So we can think of our data as being a static thing. It's sitting there at rest. It's waiting for our operation to come in. We do our operation, and then we commit and we go away. It's just there nicely for us. Failure is handled for us. So the transactions ensure that our operations are atomic. We can't have partial updates. If I update one table and update another table and that fails, the update to the first table will be rolled back. You can't, either the entire operation succeeds or it gets rolled back. And consistency is also enforced. So if my payment table references an order, that the database is able to guarantee that that order exists in that order table via foreign key constraints. Concurrency is also handled for us. Among other things, that means that there's no uncommitted reads. So you can't have something coming in and seeing data that then later gets rolled back. So if we were to visualize what this looks like, we can imagine that we've got a database, and in there are some tables. And a transaction might come in, and it says, I want to do an operation on your tables to the database. And what the database does is it's as if it materializes this view and says, okay, here's my tables. They're yours to work with. You can do whatever you want with them. You don't have to worry about what anyone else is doing. These are yours, your tables, and yours alone to do whatever you want. Another transaction might come in, and it does the same thing to that transaction. Here are your tables. You can do whatever you want. They're yours and yours alone to work with. You don't need to worry about what any other transactions are doing. And so when those transactions both commit, the database, it's through its magic, through MVCC, through other through locks and various things, ensures that those two updated states end up being merged into the database in a way that makes sense and that maintains consistency. When we move to cloud-native microservices, our current view of the world, this consistent view of the world, it breaks down. Okay, our oxygen disappears. We can no longer take consistency for granted. And so the problem is that when you use microservices, each microservice should have its own database, its own state. There was an article published by ThoughtWorks recently and basically said, if you're sharing a database between all your services, you don't have any decoupling between services. You've just got a more complex deployment. You don't have microservices. Microservices means that each service has its own database. So you've got multiple databases, and this makes the world hard. Because you've got multiple databases, you now have many states. Now, within each database, you can have an ACID transaction, something that's consistent, but you have multiple versions of these. You can't have one consistent current view of the world. So each different service with its own database has its own idea of what the current state is. And they don't all match because transactions can't span services. And so we can't think of our current state as being this thing that's in rest, waiting for us to make a request on it. We have to acknowledge the moving nature of the system. Our data we've got some data in the database, but there are currently other things happening in motion. We've got to think of our database, our data as being in motion. Failure is not handled for us. Okay, if I do an update on service 1, if I tell it to do an update and then it's part of my business operation, I need to then tell service 2 to update. If the service 2, if that fails for some reason, maybe there's a network outage, whatever, then that's not going to succeed, but you've still got the update that happened on service 1. So what do? Do you roll it back? What if you crash yourself? And there's no enforcement of consistency. If you've got two different databases, you can't have a foreign key constraint from one database to the other. It doesn't work that way. And concurrency is inherent in this system. So when an operation comes in and does an update here, it then takes time for that to propagate here and time to propagate things. It's where we had atomic operations where it was like each operation happened instantly in a monolith. We now have operations taking time to propagate through our system. So this is what it might look like if we were to visualize it. We've got all our services, and an operation comes into and is handled by service A, and another operation comes in, is handled by service F, and these trigger operations, updates on other services, so B and E get updated. And then we've actually got an out of order operation, so E was updated first by the second one, and B was updated first by the first one, and then they reversed and did the other thing. So now, are those operations still valid because the state's changed? What happens if we do this operation and G crashes? Maybe it's unable to handle the operation because its database goes down, or it runs out of memory, network goes down. What does that mean for the updates that we've already done in all these other services? I mean, should they be rolled back? Should we retry on G? Whose responsibility is it to make sure that that happens? Maybe we say, well, A received the request first. It's its responsibility to coordinate everything, okay? But the thing, failures often don't happen in isolation. You have, data centers with racks of servers, and often like a whole rack will go down due to network problem or power problem. And what if A and G were on the same rack? So now our coordinator's gone. What do the rest of the services do now? Do they even know that something's gone wrong? And of course, the second operation here has already done updates. Depending on updates that the first one has done, what does that mean for its updates? Maybe they're now invalid. So the integrity, the consistency of our whole system is now called into question. What worked when we used monoliths will not work in cloud-native microservices. Okay, we cannot rely on consistency in the same way that we cannot take consistency for granted. So examples of things that do work in monoliths, CRUD works, okay, because CRUD depends on a single consistent state. You do an update here, you do an update there, and they can be dependent on each other, but because you've got the database managing that, it makes sure that it's fine. It does that through relying on transactions, so we can rely on transactions to clean up after ourselves and make things consistent, but that depends on a single database. And for all this, we can do REST. And REST works in monoliths because we have this single database, it can manage the failure. Okay, REST has nothing inbuilt to manage failure. If a REST request fails, there's nothing's going to retry it for you. Nothing's that's going to try and roll it back for you. But that's okay when you have a single database because the database can manage that for you. When we move to cloud-native microservices, we need a different approach. And so events is an answer to this problem. Events convey facts. Okay, so if I were to say that this order is currently submitted, okay, that's not a fact. Or if I say that this order is in the submitted state, that's not a fact. Why is that not a fact? Because while I said that, something could have come and cancelled it, and it could be wrong. I don't know for sure that it's currently that, because these services are independent. Okay, so current state is not a fact. What is fact is events that happen in the past. So, for example, the user submitted the order. That's a fact. When the user submits the order, it's a fact that they did that. That can never be invalidated. Even if they go and cancel it, well, that doesn't change the fact that they submitted it. In fact, they can't cancel it if they didn't submit it at first. So that submitted fact always remains true. And so if I receive an event, I can guarantee, I can rely on that. I can rely that that's true. Like in a monolith, I could rely on my current state. If I receive an event, I can rely that that fact is true. We also need, so if we then embrace events, we need some way to get these events around our system. And to do that, we need at least once messaging. So if we can ensure that when an event happens, that we have a guarantee that this event will be propagated to everything that depends on it at least once, then we can ensure that our system will eventually converge on what the current state is, that our services can agree that the order is submitted or order is cancelled. And so to bring this all together, what we need to do is take a stream-centric view. We don't want to just have events just it doesn't work to just kind of magically fire events everywhere. We need to control them. So we need to take, to consider our data, rather than thinking of our source of truth, our data, what our system state is being that current state. We need to think of our data as being the events. So if you have all the events, you know what the data, that's the data of the system, that's the state of the system. Some of these events may be in REST, they may be stored in a database, but some of them might be currently being propagated through the system. Some of them are in motion. And so we have no single state. We don't have this, we don't no longer need to rely on transactions because we're not taking a single state view of the world, we're just taking an event view where we can rely on the facts that we've received. And because of this, the single state of the system is more a state of constantly converging. So rather than thinking in terms of this is what my current state is, our system is moving towards convergence, propagating. If you disconnected all the inputs from the system, if everybody stopped using the system, then sure, it will converge and all the services will agree on what the current state is. But as long as there's people using it, there's new inputs coming in, new events coming in, events being propagated, events in motion, our system will be in this state of constantly converging, never quite getting there, but always on the way there. And to do this, we need to control it, and we do this by using streams. We send our events down streams, and these streams allow us to propagate our data throughout the system. So we could visualize this. We've got service A and B, and we put a stream between them. So a stream is a pipe. Now service A does something, and it emits an event, and it puts it into the pipe, into the stream. And it does something else, and it's an event, and it puts it into the stream. And these events are now on their way to service B, and possibly other services, so it can fan out to multiple services that depend on these events. But what happens if service B, at the time that service A emits these events, has crashed? Because we're using at least once mechanism to get them from service A to service B, service A doesn't need to worry. Once it's emitted the event, it's out of the picture. It doesn't need to retry, it doesn't need to roll back. It knows that it's emitted the events, it's sent this fact, this is a fact that this has happened, and it's completely out of the picture. Service B then can be fixed and come back online at some point, and once it's done that, it can start reprocessing those events and come to convergence. So this is the most important thing that I want people to get from this presentation. If we model a system using streams, we embrace events, we no longer need a single state, we don't need transactions, we don't need to have this current state view of the world, and so we can take eventual consistency for granted. So when we moved from monoliths to microservices, we lost the ability to take consistency for granted. But streams gives us that back, allowing us, once again, to take consistency for granted. And what that means in practice, as a developer, you don't need to worry about failure. You don't need to worry about handling failure. You don't need to worry about handling consistency. You just need to worry about your business concerns, which is what you're meant to worry about as a developer. And the architecture or approach that you've taken will worry about consistency for you. So what does this have to do with Jakarta EE? Currently, JMS and MDBs are the best that Jakarta EE has to offer. And while all these things can be achieved using them, they are rather heavyweight. MDBs require a lot of kind of code around them. They were designed for a time where you had multiple models, so you had a monolith here and a monolith there, and you had a very heavy weight. So this might be maintained by a business unit of a very large business unit, and this one by another very large business unit. And conceptually, you had a very heavyweight transfer of, now this process is going to be handled by this system over here to do that. Whereas when you move to streams with microservices, you now have a single operation will consist of many events, potentially tens, 20, 100 events, all going through it, all going through many different services. And so you need something that's much lighter weight than what's previously offered. So there are new efforts in MicroProfile to change this. So the first thing that we've done is we've created an approach to reactive document that guides adoption of reactive features. So when I talk about streaming and maintaining consistency, I'm really talking about reactive principles that allow you to build systems that are highly decoupled. And this reactive document is going to help guide the creation of future specs and updating of existing specs. The MicroProfile Reactive project has been started, and this has two sub-specifications. The first is a project for manipulating streams. So when I want to have a stream of data and I want to do an operation on it, a map or store something to a database or filter, this library does that. And then the other sub-project is a specification for asynchronous communication called reactive messaging. And so this is about communicating between services and getting events from one service to another. There's also some future possibilities, and there's been a lot of discussion on the MicroProfile mailing list just in the past few weeks about this. Event-sourced entity support. So actually, rather than storing your data in tables, storing the events and then computing the state from the events. And publishing entity streams, so CQRS, where you separate separate your read-side model, the entities, the things that are able to validate and produce new events from the things that then go and query them and tell what the current state is. So now we're going to move on to the demo. Now, the demo is, I'm going to show a sample app called Online Auction. It's an eBay clone. It's not quite up to competing with eBay, but it will get there someday. None of these specs that I've just talked about actually exist yet. Okay, so I can't run a Java EE server and demonstrate it to you because the specs don't exist. As I said, I'm the co-creator of Largom, and Largom implements these principles. And so I've gone and implemented the specs in their current form very early. Everything could change, but in their current form, I've implemented them on top of Largom. Then I've ported this online auction demo app, which actually exists as a demo app for lots of other things, to use these new specs. So here's our online auction app. It's very pretty. I can create an item. I'm logged in as Mary at the moment. So Mary is going to sell her bike. It's a red bike. We're in Europe, so let's use euros. And 10 seconds probably too short for this auction. We'll go 10 hours. So I'll create it. And once I'm happy with it, I'll start the auction. Now I'll log in as someone else, very secure. You just select your user from a drop-down. And I'm going to search for that item. So I'm logged in as John now, and I'll search. and I can see there it is, my bike, there's our current price, and so I can click on it, and I can place a bid. I'll bid 10 euros. And like eBay, the minimum price was 50 cents. You don't actually bid the current price, it automatically increments for you as other people bid against you. So if I log in as myself and I place a bid of 5 euros, we see that's been accepted, except that it's automatically outbid by John because his maximum bid was 10 euros. So I'll place a bid of 20 euros and that's been accepted 50 cents more than John's highest bid. So the current price is 10 euros 50. So if we go and search for the bike again, we can see here, there's the bike, and we saw before that the current price was 10 euros 50, but it's not showing any current price here. There must be a problem. So let's go and have a look at the code. So this is in our, we have a number of services. One service is an item service. That's what handles creating the item and describing the item. Another service is the bid service. It handles accepting bids and managing the auction. And another service is the search service, and it handles maintaining the search index of all events. And the search service does that by subscribing to a topic by subscribing to the events coming from the item and the bid service. So since the price isn't being updated in the search service, there must be a problem with the bid events that are supposed to be reaching there from the bid service. Here is where the search service subscribes to the bid events. So we can see here, this is an application scoped bean and CDI, and we can see this at incoming annotation. So this is part of the messaging spec, and it's saying the topic is the bid events. And it gets the bid event, and it does converts it to a document. It then persists it. It's asynchronous, so it's using a completion stage to represent the result, and then it returns that result. Now here, because the completion stage, because this code looks almost identical to the code handling the item events, and we know that the item events are getting there because the bike does come up in the search index in the first place. It's just the price that's not being updated. It's probably not in the search service that the problem is. So let's go and have a look at our bidding service where the events are being published. So you can see I have this method here called publish event log. And in this case, it's not taking a parameter, rather it's returning a processor, which is a Reactive Streams thing. A Reactive Streams, it has an input and an output, and the input is auction events, and the output is bid events. Now, auction events, the bidding service here is using event sourcing. So with event sourcing, rather than persisting what the current what the current winner is and what their bid is, you just persist all the events. So this person placed this bid, this person placed that bid, this person placed this other bid, and then whenever you need to look at what the current price is, you simply load all those events, replay them to get your current state. And so because we're storing these in an event log, we can consume them as a stream of auction events. And so this is, we then use, this is the reactive stream, MicroProfile Reactive Streams spec for manipulating these events. We create a builder that's going to take the auction events as an input. We filter them because not all the events that we persist in our own database we necessarily want to publish to the world. We only, in this case, we're publishing bid placed and bidding finished events. And then we convert them to an outside representation of the events. So just as you wouldn't return your JPA entities directly from a REST service, you convert it into some other object that represents your external API. We're doing the same thing here. We're converting our internally persisted events to something that semantically represents the same thing, but is more suitable for a public API. Now you may have noticed there's no annotations on this, and that's actually the problem here. So let's add them. This page publisher is going to take as its input, as its incoming stream, the event log. So those auction events, it's going to read them from the event log. And then it's going, the outgoing, so the things that the processor converts them to is going to be published to Kafka and to that bidding event topic. So now, once that's saved, Largom supports hot reloads, so I don't need to do anything, I just need to save it and it should be reloaded. Now, when I search here, the first thing that I'm probably going to have to do is a database migration, because I forgot to have those annotations there before, and so of course my search service is in the wrong state. All the future things, of course, that's going to work, but the stuff that's in the past, because I had this bug there before, I'm going to have to fix that up, right? There's no way that the current price could be shown there when I hit search again. That's just not possible. Well, yes it is. You see, what's happened here is because I've used streaming, I've got this property in my system now that it can self-heal. Of course, the actual bug where the annotations weren't present, the system's not going to fix that itself. But once I fix that bug, the actual data, the things that were inconsistent as a result of my bug, they fixed themselves. I didn't have to go and write a database migration and work out, okay, which events didn't make it to the search service, do I need to republish them again? That automatically happens because of this architectural approach that I've taken. I'm able to take eventual consistency for granted. So using streaming, you no longer need to worry about handling failure. You no longer need to worry about handling consistency. So in summary, monoliths have allowed us to take consistency for granted, just the same way that we take oxygen for granted. We need consistency, and they've let us not worry about it. But when we move to cloud-native microservices, this consistent view of the world breaks down, and what worked for us in monoliths will not work in cloud-native microservices. If we model a system using streams, we embrace events, okay? Our data becomes the events, not what's stored in the database as the current state in the tables, but the events themselves, they're our data, they're our source of truth, they're what we can trust. We no longer need a single state. We don't need ACID transactions to give us this illusion that there's a current state that we can depend on. And by doing that, we can take eventual consistency for granted. We have a system that self-heals. We don't need to be coding in retry logic, rollback logic. It's done for us automatically by virtue of the architecture of using streams, of this constantly converging, moving, data in motion view of the world. And I hope you've seen that Jakarta EE is on track to helping you transition to this new world. So thank you for listening. The specs themselves are available on GitHub. So github.com, Eclipse, MicroProfile, Reactive. Please get involved. If you are interested in this at all, even if you have never done anything to do with reactive or messaging or events before, what we really need is people to go and ask the questions. What does that mean? How does that actually work? Because it's important that we get validation from people as to whether this will actually work when it goes out into the real world. We have a weekly hangout. The time of it's about to change, but if you subscribe to the MicroProfile list, you'll find out what the time of that is. This actual demonstration that I've done, you can find it at github.com/jropus/streaming-new-Jakarta EE if you want to just play around with that demo app. If you're interested in more about what Reactive Streams can do for Jakarta EE, there's a blog post that I published about four months ago probably the best thing to search for is James Roper, Lightbend, Reactive Streams, Jakarta EE, unless you can memorize that address. But it goes through a whole broad range of specs and possibilities for how streams can be embraced in Jakarta EE. So thank you for listening. Any questions? Yep. Reactive Streams itself is a specification for different streaming technologies to integrate with each other, and that's definitely already working in Lagom. These annotations, the messaging spec, I mean, the code's there up on GitHub, but it's not officially released. It's and it's going to change, like where these specs are in process and in progress, and things about them will change. There's not even really a way yet to specify to configure where your message broker is and stuff like that. So I'm hoping something will be that we'll be able to release a 1.0 by November this year for the spec, and there should be something corresponding running on Lagom then. Yep. Yep. The question is, how are the events stored in the bidding service? So they are stored using something called Akka persistence. It supports multiple backends. In this case, I'm using Cassandra, and basically it's a table in Cassandra, and all the events are stored indexed both by the entity ID, so that's the auction ID, so that you can replay the events for a single auction to get the state for that auction, as well as being indexed by the offset of the event, so that they can then be published to the message broker.